size and it's upside down. Well, in my picture, where would that be located? Well, it's 40 from there to there, so the focal length of the first one is at 20, it's halfway in between. This is at 30, so it would be about right here. And so I've got an object, an image, that's about at that location for the first lens. So I'm not going to try to draw all the rays and everything to show that. So that's where the first object is. Here's the first image. Well, if you've got a double lens system, the image of the first lens becomes the object of the second lens. So if this is the first lens, image is at 30 centimeters. This is in relationship to this first lens. How far is this from the second lens?
9.
What is that distance?
10.
And what side of the lens is that on? Front or back? Anyway, my drawings, I'm going to go left to right on everything. So for the first lens, here's front, there's the back. Front side of the second lens is on the left of it, and the back side is on the right side of that lens. So this image is on the front side of the second lens. But this image becomes the object of the second lens, so that second lens object distance is going to be plus 10 centimeters, since it's on the front side of that lens. So now I can say, well, okay, the second image for the second lens, then is 1 over the second object distance plus 1 over Q2 equals 1 over 30. I'll solve that for Q2. Okay, so 1 divided by 30 minus 1 divided by 10, which gives me, I'm going to take the reciprocal, right, of that answer, so that gives me minus 15 centimeters. Well, for the second lens, where is a negative image distance? It's on the front side, and 15 centimeters, so that means that second image is located about, say, go a little better here, about at this location, 15 on the front side. What's its magnification? So minus the negative 15 over positive 10, which would give me then a plus 1.5. So it's 1.5 times bigger than its object. Well, its object was pointing down, and therefore this is also pointing down, and it's larger. So there's my Q2. Again, just a sketch of what's happening there. How big, and this is now the final image for the two lenses. How big is this image compared to this original object? You know, if you took a height of it, if this was 1 centimeter high to start with, then this first image would only be 0.5 centimeter high. 0.5, but this is 1.5 times bigger than the 0.5, and so 0.5 times 1.5 would then be 0.75. So this is 3/4 of the size of this original object. Now that would make a good microscope or telescope, you know, but just here's these two lenses. Here's some numbers I give you to start with. Where is the final image? What's the final magnification? And the easy way to do the final magnification for double lenses, and we want anything to do any more than 2 lenses. Total magnification is the product of the individual magnifications. So I've got negative 1/2 here and a positive 1.5 here. So the total magnification, negative 1/2 times positive 3/2 fraction there. And so that's a negative 3/4, or if you want to, that is a decimal, negative 0.75. So it's upside down and 3/4 the size of the original object. That's what you're doing there. Well, for this one, numbers I gave you, the first image was in between the two lenses. And so that second object distance was how far are the two lenses apart, subtract that first image distance, and that was the distance for the second object, and it was on the front side, so it was positive. But it doesn't have to end up there. I can move this in. Put it, say, that first object is going to be at, and let's make it at 22 centimeters. Well, now where does the final image end up, and what's its total magnification? So I've got 1/22 plus 1 over the Q1 equals 1/20. So 1 divided by 20 minus 1 divided by 22, take the reciprocal. Q1 is going to be 220 centimeters. And that's positive 220, which means, here to here is only 40. So from here, 220 is going to be way out here somewhere. Magnification minus the positive 220 over the 22. So it's negative 10. It's upside down, but it's 10 times larger. So that's some real big image out here. But again, this image is the object of the second lens. Now, in reality, this image never appears. Because before the light can get out to there, it's going through the second lens and creating the final image. But we can still work through this pretending like the second lens isn't there. So here's our first image. How far is it from the second lens to the first image? From here to here was the 220. Here to here is 40. So this distance must be 220 minus 40, which would be 180 centimeters. That's going to be the location of the second object in relationship to that second lens. So my P2 is going to be the 180, but which side of the second lens is known, front or back? The back, and so what's the sign if it's on the back side of the object? Conventions here, that's going to be a negative 180 for that second object distance. And so now I can go through my equation again and say 1 over negative 180 plus 1 over the Q2 is equal to 1 over the 30 for the second lens. I want to solve that for Q2, so I've got 1 divided by 30, subtract 1 divided by negative 180, so that's like plus 1 over 180. Take the reciprocal, and my Q2 then is positive 25.7 ... It's some fraction of 7. I recognize that anyway. That's rounded off. What's the magnification? So minus the 25.7 over the negative 180. And so that's going to give me a positive 0.143 It's positive, which means it's going the same direction as this object, which was the image for the first one. That's pointing down, but it's only about 15% of it. And it's at positive 25, so it's somewhere in here, and it's going down like that. What's the total magnification? Well, then that's my negative 10 times the positive 0.143, and so that's going to be approximately negative 1.43. So it's almost 1.4 times bigger than this original object. And it's on the front, the back side of this second lens. So, yeah, if I put a screen at this location, that image of the original object would appear on the screen. It's a real image. That first one we did with the final image ended up in between the two lenses on the front side of the second lens was a virtual image then. But yeah, light's still going through the second lens. It's just not forming an image on that back side. Okay, so you could have the the first image end up on the back side of the second lens. Then you're going to have a negative object distance for the second lens. If it ended up in between, the first image was in between the two lenses, now you're going to have a positive image object distance for the second lens. The other possibility, what if I put this at, say 18 centimeters? Well, now it's inside the focal length of that first lens. So I've got 1/18 plus 1/Q1 is equal to 1/20. So 1 divided by 20 minus 1 divided by 18. Take the reciprocal, and you get negative 180 centimeters. Well, that's back on this side. It's magnification minus the negative 180 over 18, which gives us a plus 10. So it's 10 times bigger than the original object, but it's a virtual image because it's on the front side of that first lens. But again, I mean, this, you know, if you were looking through this lens from the back toward the front, toward this object, it would appear as though the image is back here. Or that would make, that's your magnifying glass idea there. You know, you've got or not the magnifying glass, anyway. It's like the microscope. So you're looking at something that's small here, but the microscope lens make it bigger looking at that point. So that's on that back side. Well, for the second lens, you know, that's still on the front side of the second lens. But how far is it from this first image over here to the second lens? From the second lens, I go 40 this way to get to the first lens, and then 180 to get to this first image. And so the total distance from here to there would be 220 centimeters. So my second object is at a distance of 220. It's on the front side, so it's going to be positive. Oh, wait, don't take the negative 180 plus the 40. Think of the distance. You know, just find that first image, and then what's the distance from that first image to the second lens. And then look to see, is it on the front side or the back side of the second lens to determine whether it's positive or negative. I can take that answer, put it back into my equation, so 1/220 plus 1/Q1 equals 1/30. And so my Q1, 30 minus 1 divided by 220, take the reciprocal, and that's going to give me positive 34.74 centimeters. Positive Q is on the back side of a lens, so that would be over here somewhere. That distance, back side of that second lens, its magnification, Q2, not Q1, is going to be minus the 34.74 over the 220. So divided by 220, and that's going to give me negative 0.158 rounded off. So it's much smaller than this object, its object, which is this image of the first lens. And so then the total magnification is the 10 times the negative 0.158. So it's negative 1.58. So it's upside down compared to that, which means it's going down. And it's about 1.5, a little more than 1.5 times bigger than this first object, the original object. Yeah, so, okay, I've got that sort of thing. Now, do both of them have to be convergent? No, they don't have to be. You could have one converging, one divergent. It wouldn't matter which one was the first one. You could still go through this process with everything. Or you could have two diverging lenses. You go through the same process. Take the first lens, the first object, go through my 1 over P equals 1 over Q equals 1 over F, find this first image distance. If it says anything about magnification for your problem, then go through your magnification equation. And then look at your drawing, see where is that first image in relationship to the second lens. Is it on the front side? We got a virtual image for the first lens, so it's that distance plus the distance, separation distance between the lenses for your second object distance. If it's in between the two, it's the separation distance minus the first image distance. That first image is on the back side of the second lens, then it's that distance minus the separation distance to find that second object distance. But the first image is the object of the second lens. So how far is the first image from the second lens? With plus or minus on it, depending on whether it's on the front side or the back side of the second lens. Not where it is in relationship to the first lens, but where is it in relationship to the second lens. Then go through my equation again to find the second object distance, which is then the final, or the second image distance, the final image of the two lens system. And if you need magnification, you go through that again. And if you're wanting the total magnification, what's the final image compared to the original object? Just multiply these two magnifications for each lens separately. And that gives you then what the that final magnification is. The Q2 is where the final image is in relationship to that second lens. So if you've got a double lens system, you're basically going to go through this equation twice. You may or may not need this depending on whether it's asking you about magnification. But that's the basic process in all of these double lens type problems. I mentioned that there was an equation for to calculate what the focal length of the lens is, depending on what the radius of curvatures of the different surfaces are that make up the lens. Which then eventually leads us to, if you've got these double lens type systems, but they're not really separated by anything. What's the total focal length if they're just like stacked right next to each other? For those who came in late, we're thinking of these as what are called thin lenses. Thin lens, very thin, the thickness is small compared to the diameter of the lens. Well, if you got that, but you've got, say, multiple lenses right next to each other with no real separation distance. So like the high-end cameras might have a converging lens, and then you've got a diverging lens, say, right next to it. You might have another converging lens, and these could have different focal lengths, depending on, what negative or positive, what kind they are. But you could have several of these things stacked together. I was reading about Canon camera one time, and it was talking about the lens in that, and the that lens, whatever focal length it was, it said like 7 elements in it. So effectively, it was like 7 thin lenses all stacked right next to each other. And part of the reason they do that is to give you better pictures, which I'm going to talk about in just a second. Okay. But if you've got something like that for thin lenses, to get the total focal length of the whole thing, the effective focal length of all of this, you'd go through this equation. And more than that, just by the dot. So it's like doing, like 10 resistors in parallel. What's the total resistance? So 1 over the total is 1 over the first one plus 1 over the second one plus 1 over the third one. And you get that, all of them. Or capacitors in series. Same sort of equation. That would be if they're stacked with no separation distance. By the way, the reason they would do that, I mentioned that, like for the mirrors and also for the lenses, if you got a source or an object that's infinitely far away, rays coming in parallel should focus right at the focal point. But because these are spherical surfaces, and you go through all the real fine detail of measuring the angle of refractions and all of that as it goes through air to glass back to air, the farther off axis you get, the less they focus right at that single point. So you've got like one converging lens, here's your axis, rays coming in parallel. If they're pretty close, okay, they're going to go to that focal point. But if they're out further, they may not go exactly to the focal point. And so what you get is a blurry image right at that point. Not all the rays are focusing right at the point. Well, and again, the spherical surface is the easiest thing to make, whether it's a mirror or a lens. Relatively, they could do that back in the 1700s when they first started to make lenses. So how do you try to correct for that? Well, one way you can correct for it is basically to limit how much opening you've got that the light's going to go through, especially with lenses like camera lenses. When you take a picture, the camera opens up, the lens opens up, allows light through, and whether it's going to film or the CCD for digitals, it allows the light through onto that surface that you're going to take a picture of. And you want your image to be focused on that surface. No, it's not infinitely far away. But if I can limit that opening, the size of the opening, so if my opening here only goes to there, it's cutting out all this light here, and therefore it's more focused at that point. Well, but you've got to, allow at least a certain amount of light in to get a picture at all. First time my wife and I went to Alaska to see the aurora, I borrowed a digital camera from the school. This was not much of a digital camera. Your phones are much better than that one was. But I borrowed it, And I started to use it, but this is happening at night, and it's not really bright. Some of the pictures you see are bright, but that's because they allowed a lot of light to come in. I just didn't even use it. I used my film camera that I had, which was a better camera. But I had to leave the camera open, the lens open for like 25, 30 seconds in order to get enough light onto the film that you would get a picture then as opposed to just darkness. So the narrower the opening that you make it, get rid of this, which what's called spherical aberrations, because of this spherical surface. You've got to leave it open longer so that it gets enough light onto your surface that you're going to get the picture on in order to get a good picture. So there's a trade-off there. You don't want this blurry image because light's too far out here on away from the axis, but you've also got to get enough light going through here in order to create the picture right there where your film or your digital array is at that point. And if you have to leave it open too long, okay, well then, especially if anybody's moving at all, you get a blurry picture because of their motion. If you've left the thing open too long. Those pictures I've got of the aurora, they look pretty good. You leave it open long enough, you start seeing the colors that are being created on the film then. But I can, because I was there, I know that it's slightly blurred. Because while I was leaving it open for that, say, 25 seconds, the aurora up in the sky was moving slightly. And therefore it got a blurry sort of a picture. Now, if you're going to take a picture of your kid out there, at a soccer game or something, you want to take it at a quick opening, very quick, so you don't get a blurry picture of the person running across the ground or something there. And so our cameras, in fact, I'm not sure about the cell phones, but it's probably the same thing. They don't have you don't have really any control of how long you can leave that if you're just taking a single picture. Now, if you're taking a movie picture, they can do that too. Okay, that's a different thing there.
Actually, now they have, like with the new phone that I got,
Mhm.
you can adjust the shutter speed.
The shutter speed. So they're, they're starting to try to catch up with the physical professional type cameras. So you adjust the shutter speed, how long is it open? You adjust the size of the aperture you're talking about, how wide is it open? Generally, if the light's dimmer, you open it wider. But you don't want this, what's called spherical aberration, blurriness. Well, but also with lenses, remember different wavelengths, different colors have different indexes of refraction. And so even if you don't have any problem with the spherical part of it, if you've got white light coming in parallel, well, the violet bends and it would focus at a particular point, but the red doesn't bend as much. It's got a smaller index, so it doesn't bend as much. The angle doesn't change as much. And therefore the red might focus, say, at this point. Oh, that's highly exaggerated. So where do you put your film or your CCDs or whatever in order to pick up all this light coming in? Do you put it where the violet is in focus? Do you put it where the red's in focus? Well, most cameras are going to put it halfway in between. So that, okay, the violet's not as much out of focus as it would be if you put it where the red was, or the red's not as out of focus as it would be if you put that plane where the violet was, but they're both a little bit out of focus. Now, again, most of us, we don't notice that. But if you're a high-end photographer, you know, you're gonna be looking for that sort of thing. What that's called is called chromatic aberration. Chromatic for color. So how do you correct for that? You know, the spherical, okay, just narrow down the opening, don't allow light to come in too far away from the axis. With chromatic aberration, that's what a lot of these multiple lens type systems are doing. So the light coming in to the first one, you know, the violet and the red separate. But then, say, going through this one, it has a different index there, and so it's going to bend them differently. And then going through the next one, it'll bend them differently, whatever. And then hopefully, when you get over here, then all of those colors are much closer together than they would be if it was just a single lens with a single index. And so they stack these thin lenses together in order to try to take away some of that chromatic aberration, the deviation of the different colors as they go through the lens. And again, the high-end photographers, they want to be able to try to correct for that. These aberrations that cause blurriness or something that's not exactly perfect in your picture that you're taking, there's at least 7 of these things that, you know, if it's a really high-end person would be looking for. The spherical and the chromatic are the two most common. If the lenses aren't exactly spherical shaped. So if the curvature is different this way than it is that way, then you have astigmatism, which I have in my eye anyway. I don't know about y'all, but I've got some astigmatism. And so in my glasses, they have to curve it slightly differently horizontally than it is vertically, so that as the light goes through the glasses, through the lens of the eye, gets to the retina, and it's more correct the way it's supposed to look at that point. You know, and so you can have various things going on like that. And that's the only other one I know a name for. I know there's other ones, but I haven't studied it enough to know what all those other ones are. But I think basically it's not a perfect picture if you've got these aberrations. And you've got the spherical aberration, you've got the chromatic aberration. Spherical because you've got a spherical surface. The light's either going through or reflecting off of it with mirrors. Chromatic, the refraction of light as it goes through the lens, or the different index going from air to the lens back to air, is again